Hello, my name is Thomas Rodriguez and I will be going over Lab 6 for Physics 2212. So to introduce this lab, the purpose is to observe the behavior of a magnet that would fall down an aluminum tube. For the fundamental physics principles, the first one is Faraday's law, which states that in a conductor, a changing magnetic field creates an electromotive force, or that EMF is equal to the change in flux over time. And then there's the Biot-Savart law, which states that the magnetic field, it calculates the magnetic field from a constant current, which uses this formula as well as this formula as well, which is construed in certain situations. So to continue on with the introduction, the model that was used to depict the computational data time was a velocity versus time graph. Then for the system's surroundings, the system was a bar magnet, and the surroundings was the aluminum tube that the magnet would go through, as well as any other external force affecting the bar magnet. And the main result was that the average time in the experiment was greater than the average time in the tube in the computational model. So here are the details of the experiment. This was a video of the magnet going down the aluminum tube. For the initial conditions, these are just a few dimensions of the tube and the magnet itself, as well as the magnetic dipole moment from Lab 3, which we do use for the computational data. Then here are the trials that I did with my team. We did around 5 trials, and we averaged out the time that it would take for the magnet to fall for each trial, and then we got 1.33 seconds. So for the coding, we first defined the dimensions from the initial conditions, and then created the bar magnet visualization, and then we defined a function for the magnetic dipole, using this formula that was over here, this one. Then we also made a function for the change in magnetic flux. So here, this was where we calculated the forces. So first we have gravitational force, and then with this for loop over here, we calculated the magnetic force, and then over here we added the gravitational force plus the magnetic force to get the net force, and we did velocity position update for the graph, and based on the graph, we were able to get that the time in the tube for the magnet would be 0.911 seconds. And basically to compare the two values from the main result, again, the average time from the experiment or the trials was 1.33 seconds, and the average time based on this computational model was 0.91 seconds, which it could have been more accurate, but it's at the same time, it's not like too different. So to conclude, some assumptions I made was that there would be no outside forces other than the gravitational force on the magnet and the magnetic force caused by the aluminum tube. Some possible errors was that there were some human errors when measuring the time for the trials or holding the tube, maybe at like slightly at an angle. And then also there could have been magnetic forces from phones or other electronics. For the what if question, what if the resistivity of the conductor were reduced as close as possible to 0? And how would the dynamics of the falling magnet change? Well, I believe that since there's a decrease in resistance, there would be a decrease in resistance that would lead to an increase in current according to this law here, that voltage equals current times resistance, meaning that the force opposition of the gravitational force of the magnet would be stronger, and it would cause the magnet to fall with less velocity. For the other what if question, what if there were holes or slots cut into the tube? How would this affect the ring current? Well, because there would be less current from the rings, because since there's holes, then this would cause less magnetic force. And that concludes this lab. Thank you for listening.